Lesson 2, Part 3, we are looking at the limit definition of the derivative. So to do that, we need to set up our coordinate plane so that all the notation can be in place. So let's begin. You see a curve here in blue. We're going to call that curve F, and then you have your coordinate plane. So if we start with X, then where we have X, that means there's a point, and we can call that point X, comma, f of X. If I label that on the y-axis, we have f of X over here. If I travel a certain distance from x to this next value, or this point, then I can call the distance that I'm traveling delta x, which means that this point, this x value would just be called x plus delta x. So we've got x, that's our first x value for x comma f of x. And then I've got my next point that I'm looking at, which is here, which I'm going to label on the x-axis as x plus delta x because it's a delta x distance away. So if I do that, then the point here would be called x plus delta x, that's my x value, comma, f of x plus delta x. All right, so this is just the setup. These are normal points, but instead of calling these points anything that we normally would do, we're changing them up a little bit using this notation. So we've got the notation, and we're ready to talk about what's next. So remember, a secant line has an average rate of change if we want to look at it. So here, if I was going to draw that secant line in terms of slope, we did this the other day, then slope is f of b minus f of a all over b minus a. F of b minus f of a all over b minus a. But in this case, we used different notation. We used x and x plus delta x, and we used f of x and f of x plus delta x. So technically, this should really look like this. If it's divided by b minus a, we really are just subtracting the two x values. So x plus delta x minus x. And up top, we have f of x plus delta x minus f of x. So when we set this up, we have a whole new way to look at the average rate of change, or my secant line. I can simplify this a little bit, which I'm going to do here, and we actually get the following: f of x plus delta x minus the function f of x all over, if we have x plus delta x minus x, notice they can cancel out, all over delta x. I want you to freeze the video and write down this right here. This is the average rate of change for a secant line. But what we want, if you remember in our prior conversations, we don't want the secant line. We want to pretend that that delta x gets closer and closer and closer to 0. Because if we can get the distance between 2 points closer and closer to 0, then we can get to what would be a tangent line. And since this is slope, we want to get the slope at an exact point. So how do we do that? Well, we do that by trying to make that secant line have 2 points that are much, much closer together. Well, ladies and gentlemen, we have talked about the limit, right? And what we're asking you to do here is get delta x closer and closer to 0. Get the distance between those two x values as close as possible to be 0. So in terms of a limit, we would say the limit as delta x approaches 0, and we would just write f of x plus delta x minus f of x all over delta x. And this, ladies and gentlemen, that is the limit definition of the derivative.